On September 2nd, 2023, just a fortnight after India created history by landing near the lunar South Pole, ISRO launched another very important mission, Aditya-L1, India's first mission to study the sun. Hello and welcome to The Print. My name is Soumya Pillai. I'm a senior assistant editor here. It has already been a year since the launch of Aditya-L1, and we thought there would not be a better way to celebrate this major achievement than by speaking to the scientists who made it happen. Today we have with us Professor Jagdev Singh from the Indian Institute of Astrophysics. And what makes him special is that he was the first principal investigator for the Aditya-L1 mission. So basically, he was a major contributor in shaping the entire mission till the time it launched, and now it is already giving us some very, very significant data. Welcome to The Print, sir, and thank you for speaking with us.
Thank you.
Sir, I will jump right into the questions. You were the first principal investigator of the mission. So basically, you're among the first of the team who shaped Aditya-L1 to what it was towards the end. Sir, could you tell us a little bit about the initial phases of Aditya-L1 and how the mission was conceived itself?
You see, I had a lot of experience of observing total solar eclipses, and I had 10 expeditions. But during the total solar eclipse, we get only few moments of observations, 5 to 6 minutes of observations. Then I got the opportunity to work with the Norikuda chronograph, which is a instrument to look at the outer atmosphere of the sun from the ground, but that also has a limitation. Limitations are that sky condition prevents for long-term observations. Generally, you get observation for a few hours, 1 hour, 2 hours a day, not more than that. Sky gets bad, scattering increases, and then you cannot observe. I was observing for 10 years, and I observed for about 1,000 days. But I could get the data only for about 40 to 50 days. Okay, and that too for half an hour, 1 hour. Then I realized that we need to go to space. Ground-based observations are not sufficient to carry on the scientific observations what we need to do. We need observation 24 hours a day. There's a lot of energetic events which are happening on the sun, like CMEs, solar flares, which affect the Earth's atmosphere and the life on Earth. Okay, and the appliances, electrical grids, and other things, etc. So we need to monitor 24 hours a day. So the only way out is to go to space. With the experience of observing during the total solar eclipses and with the Norikuda chronograph in Japan, I thought we can do something different than what the Americans or Europeans are doing. Okay, and they also have the instruments in space. They are observing the outer atmosphere in space. What they are observing in the EUV wavelength and X-rays wavelength. So that has its own advantage and disadvantages. Advantage is that they can go close to the limb, they look at the disk. Okay, what disadvantage is the signal gets integrated along the length of the loop. Okay, so and it has low resolution, spectral and spatial resolution. If we go in the visible range, which they have not been observing, we thought we should do the observations or make the instruments in the which will work in the visible range in the green line and the red line. These are the two emission lines. The corona is very hot, outer atmosphere is very hot. So the oil, the atoms are ionized to high stage. That means iron atom, which is ionized 13 times, that 13 electrons have been ejected out. So we thought of observing in those emission lines. So then I floated the idea that we should have a visible emission line chronograph in space. So then there was a reluctance. That reluctance was that you are proposing in the visible range, you can observe this from the ground level itself. I said it has a limitations. Then it took about a year or so to convince the management that it is important to observe in space and the visible, and it is different from the Europeans and the Americans what they are doing. With that, I was able to convince. Then principal they agreed. Then number of proposals were uh, called for, invited from the different people by the committee. Then I made this proposal in 2006 and it was accepted that this should be done. And then it went to EDCOS, where Professor Yuva Rao is the chairman, and he set up a review committee and other thing. Lot of review committees were done. Finally, after the scientific community accepted this, and then they said feasibility study. Okay, scientifically you are okay, it should be done, but physically it is possible, feasibility study. Then I met various organizations in ISRO and explained, and then they listened to my requirement. Then they have to look after whether they can do it or not. So we had lot of meetings, our pointing accuracy, and then data download, capabilities, and all those things, etc., were discussed. Finally, ISRO said, what you are demanding is too much. It is extreme. We don't have such capability right now. We have to work very hard to develop all those capabilities. But finally, they agreed, okay, they will develop all those capabilities. And then the feasibility studies was done. They said, okay, we are ready for it. We'll develop all these facilities and it can be done. Then after that, we went back again to URO committee. So then they said about the budget. And then budget, first they gave small satellite. They agreed with a small satellite, which was a 50 centimeter with a weight of 50 kg. Then we studied that. I said we can't do this experiment with small satellite. We need a bigger satellite. And then bigger satellite was provided. Then we started working on that. And we worked for about 2 years. But in 2011, when we have procured, finalized the design, optical components, detectors, and so on. 2011, Professor Yadav said, why not go to L1 instead of low Earth orbit?
So
Previously,
just
it
for
was
the benefit, I'm sorry to interrupt you. Just for the benefit of our viewers, could you tell them a little bit about the L1 point, the Lagrange point,
yeah.
just so that there is some context to
Okay,
what you're explaining right now?
I shall do that. See, the first we were supposed to put the satellite in low Earth orbit. Low Earth orbit is about 600 to 800 kilometers around the Earth. It takes 90 minutes to make one revolution. It was supposed to be put in the polar ridge orbit, but we could not observe 24 hours a day. There were some eclipses of half an hour or so. So it was not possible to observe 24 hours. Some days it was possible to observe 24 hours, but some days it was not possible to observe 24 hours. What when Professor Yuval suggested that we go to L1, Lagrangian point, Lagrangian point is at about 15 lakh kilometers away from the Earth. It is a point where the gravity due to the sun and Earth cancels each other. That means there is no gravity and that, and it is just a point. There is no satellite. Generally, the satellite revolves around the some object like uh, moon revolves around the sun, okay, around the earth. Earth revolves around the sun, and similarly, satellites revolve around the earth. Okay, what artificial satellites? Moon is also a satellite. But here is just a point. So satellite revolves around the L1 point. That is why it calls a halo orbit. Okay, and it takes about 6 months to make one revolution around L1. Okay, so it is at a distance of 1% between the distance between the sun and Earth, and sun is 15 million kilometers, 150 million kilometers, 150 million kilometers, where the satellite is placed at 1.15 million kilometers, and then it takes about 3 to 4 months to reach the satellite, to reach from Earth to the orbit. So it reached on March 6th, sorry, January 6th. It reached on January 6th, and it was put into the orbit at L1 orbit on January 6th. Is it sufficient?
Yes, sir. Yes, sir.
Or you
Uh,
want more information?
No, 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 sir. This would be enough. Sir, if you could also tell us the importance of the mission itself, because you said that it took around 17 years from when, the talks first started in 2006 about the mission, and then in 2023 when it was finally launched. Could you tell us the significance of Aditya-L1 mission and why is it important for India?
You see, there are 7 payloads on Aditya-L1, and I am happy to announce that all the payloads are working very well. And I will talk about VLs. See, it is a mini laboratory. Actually, Aditya-L1 is a mini laboratory. It looks at the sun and its atmosphere from all the angles, and it does some situ measurements also, plasma measurements, magnetic field measurements, and other things, etc. And I will talk more about VLC. VLC looks at the outer atmosphere of the sun. Okay, generally, most of the other payloads, European and American, they were able to go only up to 1.1 solar radii. They could not go close to the sun. Okay, they could not make the observation close to the sun. Whereas we have planned at 1.05 solar radii. So our observation starts 50 arc second above the sun. Okay, why it is important is when solar flare happens, then it leads to the coronal mass ejection. It's a lot of high energy particles, and the charged particles are ejected out of the sun in a few minutes, kind of a thing, etc. So when they travel to the Earth, they damage our Earth's atmosphere, ionosphere, and which leads to kind of a damage to electrical grids and other things. So it is important to predict when it is likely to reach the ionosphere and affect the Earth. So initial phase of the CME is very important to study to predict the actual time of arrival at the Earth, or to save the satellites also, what we call space weather thing. So what happens is we will be able to get the data and predict the initial phase of CME. CME. So when CME happens, we start our observations, and then we can measure the acceleration or de-acceleration of CME. Nowadays, the prediction is has the uncertainty of about 12 to 24 hours. With the data what we get, we will be able to predict within a 3 to 6 hours. Our prediction will become accurate, and we will be able to do that. That is one thing. Another is fundamental science. The coronal plasma gets heated up from the sun. How it gets heated up is still not clear. There are models. Basically, we know magnetic field energy is converted into the heat energy. What how it is converted is not clear. So we will study how, since we will be making observation throughout the day. So far, observations throughout the day are not available. Once we make the observations throughout the day, we will be isolate which model works better, how the plasma gets heated up, how the magnetic energy gets heated up. See, it is a kind of a thing. It is like a dream. I'm talking of a dream now. See, when if it is a laboratory, lot of energy is stored into the magnetic field. If you can really find out how the energy is stored into the magnetic field, and if you can make understand, if you can release the energy slowly from that magnetic field, you can solve lot of problems of the electric electricity on earth. What it is a dream, it is not a kind of a thing which is possible now. Okay, and who expected that one day people will do about 100 years back or 150 years back? Nobody expected that people will land on moon, but now it is a reality. So things become reality. Another thing is, sorry,
No
uh,
problem.
another thing is that understanding the sun gives lot of other thing. Leave what of it is not only fundamental science. Once we understand, you see, development of technology takes place. Whatever now, due to our requirement of high stringent requirement of pointing accuracy, data download, and other things, ISO has developed a lot of expertise and involved lot of industry. Industry has also contributed a lot. So it when we launch any payload, it is not only the knowledge what we gain, it is the technological development takes place, industry development takes place. When industry develops, then general India develops. Okay, so it is a multi-purpose gain from any launch. One should not look only from the scientific gain, but look from the various other gains. Like so many things happen when industry develops. Kind of thing. Thank you.
Sir, you said that since January, Aditya has been giving out, recordings through various experiments that are on board. Could you tell us a little bit in a simplified way the kind of data that we are getting from Aditya-L1? If I'm not wrong, the mission life is like the minimum mission life is 5 years. And what is the kind of data that you expect to receive from Aditya in the coming years?
Yeah. The thing is, data. First, about few months from January, it was put. Then ISO has to look after various their own instruments in the sense not the satellite, how the data will be downloaded, what are the auxiliary data equipment. like guiding and other things, etc. About 3 to 4 months went into that, checking the health of the all the payloads and other instruments, etc. And then we started not looking at the sun. We checked whether each equipment is working. So about 2 months went into that. Okay, checking each equipment, how the data is coming, how the data download is taking place, whether the data download is whichever we get is what is expected or not. In the initial stages, there were some issues. Okay, then we have to solve those issues, kind of a thing, data download and other things, etc. Once the data download, everything is solved. It took about 6 months for us. Then we started, then there was a little bit of offset between VLC, optical access, and the satellite access. So that was corrected for it. Then, after correcting the optical access, and so that and putting the satellite and the offset position, we were able to observe the outer atmosphere of the sun. Okay, so we are taking the images of the outer atmosphere corona, where a suit is taken. Probably you will be talking to them also. They are taking the disk images, kind of a thing, etc. So they are taking the disk images in the EUV part of the spectrum. We are studying in the visible part of the spectrum. So there are different kinds of data we are taking. One is we are taking the spectra with high cadence. That means every 5 seconds we are taking one spectra in all the emission lines. So that what the data volume has to be restricted. We cannot, in 5 seconds it will generate terabyte of data, which we can't download. We can download 100 GB data only. So with 5 second interval, we make observation for about 10 minutes. They are used to study the high frequency oscillations into the solar crown. So thereby we study the existence of waves, are there waves or there flows into the solar corona. Since there's two groups, one is favoring flows into the solar corona, other groups favoring the uh, waves into the solar corona. So waves has its own characteristic, flows have its own characteristic. So we will be able to study all those things, where the flows happen, where the waves happen, since wave heating mechanism, spontaneous heating of the solar corona. All those things we will be able to study from this data. Then we are taking a cadence of 1 minute. We are taking the spectra every 1 minute. So when what that we can observe for about 20 hours a day. So when we observe for 20 hours a day, then whenever CME happens, we will be able to study the CME at what time CME happened, and then derive the parameters of CME. What are its effects? When it is likely to be reaching the Earth? Predict various things, etc. What are the see? Most of the CMEs are observed in the continuum. Okay, that continuum is a plasma which is a part of low temperature plasma and high temperature plasma. Whereas we are observing in high temperature plasma and plasma around 12 million degrees. Such CMEs has not been observed so far. So we will be observing CMEs around the clock in hot plasma, 2 million degree plasma. So that is a different thing. That is a new thing which we are going to do. So we have collected data for about something 3 to 4 months. Okay, so we are analyzing that. Okay, and we are uh, expected to have a new finding or prediction and the how CME develops or dynamics of CME in hot temperature plasma. That is what we are going to find it out.
Thank you, sir. This was all the set of questions that I had for you. Thank you for speaking with us, and thank you for telling our viewers the significance of Aditya-L1 mission. I know there's a lot of work that is happening at the Indian Institute of Astrophysics, and we are keenly waiting for more such events, more such missions to be carried out in the future. Thank you to our viewers for tuning in and joining us for this interview. You were with Soumya Pillai and Professor Jagdev Singh. Thank you for tuning in to The Print.
Thank you very much. Thank you very much. Bye.